Okay, guys, welcome. Today we're going to talk about Diophantine equations. Now, the motivation behind the idea of what a Diophantine equation is the following question. For example, if I have 20 nickels and 20 dimes and I owe you 67 cents, can I pay you back exactly using the nickels and dimes? Of course, the answer is no, right? Similar question, can you write 113 as the sum of an even number and a multiple of 6? And of course, also no, because if you have an even number plus a multiple of 6, which is also even, you of course can't get an odd number, right? Now, the idea is that these questions cannot be answered on the set of integers is the key here, right? If we had, and what I mean by integers is that you can't give somebody a fraction of a dime or something like that, because so we require those numbers to be integers. Now, we've seen similar questions before, but of course, most of the time we've seen them, they would have solutions among the real numbers. All right, so for example, when you took an Algebra 1 class, you talked about how to solve something like 2x plus 3 equals 20, and you would subtract 3 from both sides and you get 17, and then divide by 2 and you get that x is equal to 17 over 2, which of course is a real number and not an integer. Now the equation 2x plus y is equal to 0 is something that has infinitely many solutions, but we're going to come back to something like that. And then of course you also looked at systems of equations where each equation by itself will have an infinite number of solutions, but to get considered together, they have one solution that's common to both equations. Right? Now, if we come back to this single equation idea, but we require that our solutions be integers, we can limit the number, or at least the type of solutions, right? So for example, let's consider the equation 7x plus 11y is equal to 1. And we want to find integer solutions for that. Now, you could stare at this for a while and you could eventually find that x equals -3 and y equals 2 will do the job, right? Because if you do 7 times -3 plus 11 times 2, you'll get a -21 plus 22, which of course is equal to 1, right? And that's one solution that would work. Now, this would be a little bit harder to find, and of course, it would be much harder to find the solutions to something like 343x plus 507y is equal to 13, right? And that's what we're going to discuss how to do. Now, I've said Diophantine equations a couple times, but we haven't talked about what a Diophantine equation exactly is. And they're polynomial equations with integer coefficients where the desired solutions are required to be integers. So these are just the equations that we've just been talking about. Now, of course, one example is the Pythagorean theorem, even though in practice there are non-integer solutions, but there's several well-known integer solutions, right? For example, there is 3, 4, 5, right, for your x, y, and z. There's 5, 12, and 13. And then there's also trivial solutions, right? And when we say a trivial solution, we mean that they use only ones and zeros, right? So one solution, of course, is to make them all 0, and another solution is to make either x or y 0, make the other one 1, and then z would also be 1, right? And of course, there's an infinite number of these integer solutions. And we'll actually do a section on this a little bit later on, where we look at Pythagorean triples. Okay. Now, if you look at a similar equation, but instead of squaring your x, y, and z, you're now cubing them, this equation actually has no non-trivial solutions. And even more general, x to the n plus y to the n equals z to the n has no non-trivial solutions for n greater than or equal to 3. And this is known as Fermat's last theorem. Okay, but anyway, let's go back to our regular Diophantine equations. So let's consider something where we have 2x plus 4y is equal to 23. And of course, we want x and y to both be integers. Now, you might think that this, of course, will not have any solutions, and you're correct, because if you add two even numbers, you can't get 23 to come out, right? And 2x and 4y, of course, are both even. Now, is there a general thing that we can say about when a solution exists? Well, of course there is. If there is some d such that d divides a and d divides b, but d does not divide c, then there are no solutions, right? So for example, in this previous example, we had that 2 divides 2x, 2 divides 4y, but 2 does not divide 23, right? So that tells us that there's no solutions. Now, in order for solutions to exist, we need the GCD of A and B to also divide C, right? We need that to occur for solutions to exist. So let's go ahead and let's look at a couple examples and determine if we can solve them. Well, if we look at part A, we have that the GCD of 4 and 6, of course, is equal to 2, right? Because 2 is the largest number that will divide both 4 and 6. And of course, 2 divides 2, so we can solve this, right? And it's not hard to see that x is equal to -1 and y is equal to +1 is a solution. For part B, again, the GCD of 4 and 6 is still 2, but 2 does not divide 3, so there's no solution. And again, no integer solutions. You could make x 0 and y 1/2, and that would satisfy this, but we're just considering the integer solutions. Right? And then, of course, the last one, we know that the GCD is 2, and 2 does divide 4, so we can solve this one. And of course, it's not hard to see that x is equal to 1 and y is equal to 0 is a solution. Okay. And if you didn't want trivial solutions with a 0, you could have x is equal to, let's see, if x is equal to 4, then you get 16. And if y is equal to -2, that would be minus a 12. That would also work, right? So this is also another solution. Okay, so that will wrap up this video on the introduction to Diophantine equations. In our next video, we'll talk about how to solve them for one particular solution, and then we'll talk about how to find the general solution set as well. So I hope you enjoyed, and I'll see you next time.